Let's look at a few more examples of factoring trinomials of the type ax squared plus bx plus c using the trial and error process. Example number 3 is 6x squared plus 21x plus 18. Notice that unlike our previous examples, the terms of this trinomial do contain a GCF other than 1. All three terms are divisible by 3, so we'll use the distributive property to factor out that 3. And then we'll look at our trinomial 2x squared plus 7x plus 6 and try to factor it as a product of two binomials using the trial and error process. Looking at our first term, we see that 2x squared, the value of a there is prime, so we know that the only way to factor 2x squared is 2x times x, so we can start with that. And then looking at our constant 6, there are two possible factorizations, 1 times 6 and 2 times 3. From our middle term of 7x, we see that since it's a positive number, we need plus signs in both of our binomials. And also, since the absolute value of 7 is relatively small, it seems like 2 times 3 might be a reasonable first choice in terms of a guess for our factorization of 6. If it's not correct, if it doesn't work out, we can always try 1 times 6 as a second option. But let's be careful using the 2 and the 3 from this factorization. Notice that if we put the 2 in the first binomial along with the 2x, we would see that that binomial now has a greatest common factor of 2. And this is impossible because once we've factored out the GCF of our trinomial, no binomial factor can contain a GCF other than 1. The reason for this is that if the binomial has a factor of 2, then it follows that the original trinomial should have had a factor of 2 as well, and we should have factored that out in the first step. Since we didn't, we know that 2 is not a possibility for this binomial. So instead, let's put a 3 in the first binomial and a 2 in the second one. And let's check our outside product, which is 4x, and our inside product, which is 3x. The sum of those is 7x, which is what we were looking for. So we found the correct factorization of our trinomial. Remember to include the GCF of 3 along with both binomials in the answer. Let's go to example number 4. 5n cubed minus 16n squared plus 14n. Again, we see a greatest common factor. In this case, it's the variable n, so we'll use the distributive property to factor it out. And now we'll think about the trial and error process and try to come up with two binomials that have a product of 5n squared minus 16n plus 14. Once again, we are fortunate to have a prime number as our coefficient of n squared, so we will factor that as 5n times n. And noting that we have positive 14 as our product for c and negative 16n as our middle term, we know that we need two minus signs. And then for 14, we'll either fill that in with 1 times 14 or 2 times 7. Let's check some options. Given that our middle term is 16n, let's first try 2 and 7. If we place the 2 and 7 in these locations, note that we would have 5 times negative 7, which is negative 35. That's not anywhere close to negative 16. That will not work for a correct middle term. But if we reverse them, now we have 5n times negative 2. That's negative 10n. And then in the middle, in the inside multiplication, we have negative 7n. So negative 10n, negative 7n, total of negative 17, not quite where we wanted to be. We wanted negative 16. Since we have tried both possible locations for the 7 and the 2, we can eliminate that factorization of 14 if we know that it's not correct. So let's go back and reconsider 1 times 14. Well, I hope you can see quickly that we don't want to put the 14 on the second binomial because 5 times 14 would be 70, and that's again nowhere close to 16. That one can't be correct. What if we try 14 in the first binomial and 1 in the second binomial? we would have negative 5n and negative 14n. That's a total of negative 19n. This also is incorrect. Our middle term that we were looking for was negative 16n. Since we tried all the possibilities and none of them worked, we must conclude that the trinomial 5n squared minus 16n plus 14 is prime and cannot be factored into two binomials. This means the factorization of our original trinomial is the one we achieved using the distributive property. Note that the original trinomial is not prime because we were able to factor out that common factor of n. One final example, example number 5, negative 12x squared minus 28x plus 24. If the leading term of our polynomial is negative, it's helpful to factor that negative sign out along with the greatest common factor, which in this case is 4. So we'll take out negative 4 using the distributive property, and then we would have 3x squared plus 7x minus 6. Let's think about factoring that trinomial into two binomials. 3x squared must be factored as 3x and x. And then for negative 6, we actually have 4 possibilities because of that negative sign. We could have 1 times negative 6, 2 times negative 3, 3 times negative 2, or 6 times negative 1. Looking at the fact that our middle term is positive 7, means we probably want to consider factorizations where the larger absolute value is the positive number. For example, 3 and negative 2, or 6 and negative 1. However, 7 is not a particularly large number. The absolute value is relatively small, so with that in mind, choosing factors that are a little closer together, like 3 and negative 2, seems preferable to something like 6 and negative 1. So we're, again, using the value of b and the sign of b to really help us make a good, reasonable first guess. It's that third tip in the trial and error tips. The greatest common factor idea helps us again in this problem, because if we are going to use 3 and negative 2, note that the 3 may not go into the first binomial, it has to go into the second one. And then the negative 2 would go into the first one. We can't be certain that this is the correct factorization. It seems like a logically reasonable guess, but we can't be certain until we've checked the middle term. Well, multiplying our outside two terms, 3x times 3 is 9x. Multiplying our inner two terms, we have negative 2x. 9 and negative 2 add up to 7. That's what we were looking for. So we have found the correct factorization of this trinomial.